Hello?
It's on and it's not on. Put volume up on it then maybe? He should get it in a moment.
Hello? You got a speech? You have a speech? Oh, I mean, ถ้าอยากอ่านอะไรอะ I don't think it's a good idea if you could walk and like peek and then I don't know เดี๋ยวเอาจะเสิร์ฟให้ โอ้โหดีเลยจัง
Well, at least something works.
Yeah.
So why don't you go get started because the times are
All right, okay. Oop. Oh, it's the time. Okay, so good morning, everyone. We're from Chulalongkorn University, team 204, and we're in the 30K COTS. And today we'll be presenting about a non-pyrotechnic recovery system for high-powered rockets. Okay, so we'll be discussing about the concept, the design. There'll be two SRAT components that we made so far. One is for the ejection system of the rocket, which utilizes CO2 and a springs mechanism. And the second one is a rotary mechanism component, which acts like a tender descender. And we'll be talking about how we designed it, safety features, and our experimental data. So,
Okay, so basically for recovery systems, the traditional way to do it is to use black powder. But for us, in our case, it's kind of unique because we can't really legally use black powder in our country. So the only workaround is to use flash powder from fireworks, which isn't that scalable and is quite dangerous. So we try to also pry away from the risk of danger and also the degradation of components. And also what a problem that we might face is taxes from buying cost devices from outer sources, for example, from the US. Okay, so this is our previous year's attempt. So we had a pneumatic piston nose cone ejection system, and basically what they tried to attempt is to substantially reduce the use of black powder. But for this year, our goal is a little bit more ambitious. What we decided to do is to completely eliminate the use of black powder in our recovery system.
so just to add on, for our very first rocket for this competition, we use a pneumatic piston. So this piston is kind of heavy, but it kind of works by pushing the piston apart, and it's like a mechanical separation. So it was a start from our senior, and but it was kind of heavy, so we tried to find another way which is more mass efficient. And so let's start off with the concept. Okay.
All right, so this is our CO2 ejection system. This is called the SID, the Spring Integrated Deployment. And this is basically an ejection unit which utilizes only CO2 and springs to eliminate dependency on black powder. Basically, the benefits of that is there are no, like the reliance on pyrotechnics does not rely on any form of pyrotechnics. And also, the parts are widely available, and they're also mechanically simple. And also, um, in terms of temperature and environment, it's
Yeah. So like it was in-house manufactured, so it was not that sophisticated to manufacture in-house, and we have a 3D printed case for the servo, which activates the which unlocks the key which is locking the compressed spring, which is essentially for puncturing the CO2 cartridge. Okay, so the other one is an ISRAT tender descender. So this is, you can see the section view and the isometric view. So it works like a key, kind of like a door latching mechanism that you can see in car doors and other doors around us. So it does not use black powder as well, and it just utilizes a mechanical mechanism to unlock and lock, which in this case is locking our main from deploying until the appropriate time.
okay, so let's get into the spring integrated deployment. Okay, we're gonna start with the components. So this is the center. We have a puncture pin, and with this puncture pin, we have two main springs. We have a main spring and a rebound spring. The main spring is what drives the puncture pin to basically puncture the CO2 cartridge, and the rebound spring basically allows the puncture pin to rebound and basically clears the way for gas to escape.
So we essentially do not want our pin to, after puncturing, to get stuck in the cartridge. So that's what the rebound spring is for. And this is just a sectional view of the component. Okay, so according to the DTEG, if you're using a spring component, we gotta have two safety locks. So the safety key is just to make sure that the main key can actually move or like unlock itself for some reason, like vibration in the rocket or something like that. And the actual key which slides out and the compress spring decompresses, that's how it actually actuates. So this is the two key safety features that we thought of while designing this up. Okay, so these are the parts. All right. Okay.
Yeah, thanks.
Okay, so is it working? Yeah. It does. Okay. Okay. So these are the parts of the spring integrated deployment component. So we have a servo arm, which essentially swings the safety pin out before actually actuating the component. There's a bottom case where the cartridge mounts to the component, and there's a top case where the servo and the pin and the safety key is located. And inside this top case, there will be a compressed spring. Okay, that's the servo motor we use, and that's the case.
Okay, this is like the full assembly, and okay, we forgot to say what happens. basically the servo arm first moves counterclockwise to release the secondary safety key. Then it will move clockwise to then release the main key. And then what happens is basically the puncture pin will contract and puncture the CO2 cartridge.
Okay, so we after designing it and manufacturing it out, we actually ran lots of ground tests, including inside our own rocket. So uh, let's talk about theory first. So there's two main theory that we use. So in calculating this component, so there's moment and torque because there's a servo that needs to sweep out the safety keys, and the spring potential, which essentially is the calculating the spring that we need to use that will be able to drive our puncture pin to strike and break the cartridge seal. And we experimented in by itself first outside, then we integrated into into our rocket and see if it actually works. And as you can see in the picture, our rocket separates. Okay, so let's talk about the second SRAT component. Okay. Okay, right. So this is an overview of how it looks. So this is the case without the arms, and as you can see that picture right there, it shows how the arm is mounted. So there'll be a case and bushing for the arm to pivot around, and this is actually modular because we can use the we can use fasteners that is widely available in local stores to assemble the case, and the bushing is made from nylon in house. So we make it. We don't have to spend lots of money in ordering from outsourced manufacturers. And let's see the next slide. Okay, so as I said, we have a case. So there'll be a top case, bottom case, and there'll be a left arm, right arm, which is the main parts which unlocks and locks uh, our our links, and there'll be bushings for aligning the arms together, and the whole case is compressed by fasteners, which is available locally. Okay, so the safety features. Oops. Okay, we talk about the safety feature of the previous component, the ejection component. So we have the two fail-safe mechanism to prevent it from unlocking in high G environment. And for the second safety feature of this component, could you move? Okay, thank you. Okay, I'll tell you. All right. Okay. So for our second component, we actually ran a finite element analysis to see if it can actually handle the stresses that will be experienced in our flight conditions. And as you can see, it's k- it's it's pretty safe because little there's very little deflection, and the maximum stress is kind of not not that much, not that the material can't handle. So can next slide, please. Okay, results and conclusion. We'll talk about the results and conclusion now. So the non-pyrotechnic recovery system is reliable from ground tests, from first calculating in theory and moving into ground tests, and we have validated our system. several times, both in Thailand and after arriving here, we also validated once again. The system has the potential to be to be used in commercial rockets if we could commercialize it and find a way to produce the parts in without having any like complications. And yeah, it would be great for Thailand rocket teams to use it since it does not complicate it does not have black powder, which makes the team have to find black powder, which is illegal, and it's a gray area in using those, and it does not degrade our component. So because we use an eagle before, because it's required in the DTEG to use a COT device together with an SRAT. So what we notice from reusing the eagle every year is that the components inside degrades due to the usage of black powder corroding and oxidizing. So with our devices, we hope it would greatly reduce the degradation of the components. And yeah, that's the end of our slide. Thank you.
Good, well done. So a question would be, you mentioned you validated here.
Yeah.
Is that coming, or are you going to do that at the site, or did you, you spent a couple of days prior? When was the last time did you validate it here? I guess that's what the question.
Our system,
Yes.
like 3 days ago. Some yeah. So we like
So you won't have to do it at the site.
nope. Yeah.
All right. The other thing is repeatability. It seems like you have fairly good repeatability. In other words, you fire it, boom, done. Okay, now let's load it up again. So you just cock it.
Yeah, we reload the cartridge and then we just fire it again through the SRAT computer.
One suggestion would be to have a slow motion kind of CAD video
All right.
of that. Just, because it looks a little confusing. I understood when I first read your podium, I thought, it didn't make a whole lot of sense. There were parts and stuff, but now I get it when I see it. Flip and then this thing slides, and it's kind of like one of those little puzzles that you have.
Oh yeah. I mean, I wish we could bring like the actual thing, but it's in the queue for the safety review. So
Oh, that's why you made two of them. Or you make one out of plaster Paris or paper mache. But otherwise, good, fantastic. Should do it.
yeah.
So I have a couple, if that's okay.
Yeah, go ahead.
Yeah.
So I know you mentioned you used the Eagle before. So from that, using that, how did you determine what size cartridge you would need? Did you go with like the biggest you could readily get, or was there some math to calculate?
Like in terms of using the CO2 cartridge, the size of the CO2 cartridge, it's actually from, so we first find the shear pins that we need to use in the rocket. So the way we calculate is by the worst case scenario, we assume all the vent holes are clogged. And then if that's the case, if all the vent hole are clogged, so we assume that the pressure inside our rocket is basically at like the launch site, the ground launch site level. And once we go up to the apogee, that's as you go up, the pressure decreases. There'll be pressure difference inside and outside, which tries to separate your rocket, right? So that maximum pressure difference, from that maximum pressure difference, we find the appropriate shear pins to use with our rocket. And afterwards, we see the specs of our shear pins and see what the amount of pressure that needs to be pressurized inside the airframe to shear the pins. And from that, we just find like what size of cartridge is available in the market, and we choose accordingly.
Do you remember what size?
We use 25. I mean, it was like from the calculation, it was like 22 or something, but they do not sell 22, so we go with 25.
But if you put in a 35, it wouldn't make much difference.
It would just separate further.
I mean, yeah. So you have significant, sufficient margin to
Yep.
make this work.
The other thing is, I know a lot of teams will run like two deployments based on different computers. Do y'all have pretty much like two of these mounted in your rocket, or
No, we do have only one of these, and the other one is we're still using the Eagle.
okay,
So the Eagle is connected to the Telemega, and this is connected to our SRAT flight computer.
which one's the primary?
So how it works is like we try to actuate our SRAT like first, and then 2 or 3 seconds afterwards we activate the Eagle to see if our device is actually working in real flight conditions.
And how would you know that yours did the job?
We have a run cam on our bulkhead, so yeah,
The first competition rocket used black powder, right?
it uses yeah, a tiny bit in the pneumatic piston.
Do you know how they acquired it?
The black powder,
Yeah.
like the Wildman and Aerotech sell black powder here, so
No, but do you know how they got it in Thailand to do the testing?
they probably like bought like some sketchy crackers off the shelf, like off the some sketchy market, and they disintegrate the crackers and try to. I'm not really sure as well, cause
Yeah.
it was long time ago. Yeah.
And they had a lot of difficulties because some of the powder is.
Yeah, some of the powder really like degrades it oxidizes our component and really quickly degrade our device.
Do you remember the weight of this thing?
Of
How heavy?
ours.
Yes.
So including the case and servo and the cartridge, one of them is around let's say 500 grams at max. I don't think it reaches 500, but yeah, I don't know in pounds, but like
A little over.
yeah.
All right. Come on, Jamie, you gotta come up with a question.
I don't have a question.
Okay.
I forgot what it was. There was something I think it explained earlier.
Bird smoke. That should do it. Anybody else? Question? You mentioned the eagle. I'm not familiar with that term eagle. What?
It's one of the commercially available CO2
Oh,
injection
okay.
systems,
All
but
right.
it uses that little bit of black powder.
And it uses, okay. I think I've seen that in some of the other.
I was you've probably seen it at some point.
Right.
I was gonna say because I'm interested in a system like this for some of my personal rockets that I fly, and I was looking at the Eagle and I quickly realized that as time goes on,
It degrades really fast.
Yeah.
and trying to get a reusable system.
Yeah, so we bought Eagle 3 years ago, and every year we come to compete in this competition. But it's not illegal for us to flight test our rocket in Thailand. So we launch our rocket once a year. So in total, uh, including ground tests with Eagles, we do around 10 ground tests per year. So maybe a little over 33 times of using the Eagle, it's really bad. Like the condition right now is really bad. We have to buy a spare one for our launch every year just to make sure it works.
The materials that you're making this unit out of, is it aluminum, steel?
It's aluminum.
Aluminum.
Yeah.
Okay, light.
Like.
Good. Talk to this guy about royalties.
All right. Thank you. So are we done? All right. Thank you so much.
microphone. We all need to speak into it, even though we won't hear it. If you're using the clicker, you should be on this side of the room. At the end, we're going to scan a QR code. Otherwise, I think we're set. Hey guys, 9:30, we're going to start. Maybe stand over on this side. Yeah. All right. You want us to just speak into the mic? All right, perfect. All right, thank you all for coming. I'm Thomas. We are Cornell Rocketry. Today we'll be presenting our autonomous parachute guidance system, which we call BLIMS. I'm a mechanical member on our team, and I designed the actual mechanism of BLIMS.
Hey everybody, my name is Trevor. I'm a mechanical member on the recovery sub-team as well, and I worked on the controls for this project.
Hi, my name is Gabriella. I'm a software engineer on the software team, and I work on the software for the system.
I don't see that we have any amplification of volume. Is it all turned on?
Correct. That is going to the live stream. So
Yeah, volume's only going to the live stream.
Okay. So we've all been here. You have a beautiful lunch, your rocket, it's coming down, it looks amazing, and it winds up somewhere where you don't want it to be, perhaps in a 40-foot tree. So that was our main motivation for doing BLIMS, so what we'll talk about today are three different systems. BLIMS is an autonomous, it will autonomously steers our rocket's descent by pulling on the brake lines of a parachute to a specific GPS location that we input. The three systems we'll be talking about today, or three parts of it that we'll be talking about today, is the mechanism, the controller, and then the software that runs it.
So to give you a little bit of context about our recovery system this year, we're using a ram air parafoil. So this is fundamentally pretty different from the round canopies that are common in amateur rocketry. So like a round canopy is basically just a big piece of fabric that's inducing a ton of drag. A parafoil is pretty different in that it's filled with cells that inflate with air and actually act as a wing. So when you pull on the brake lines, they basically deform the ends of the parafoil, induce an asymmetric drag, which will give you a yawing moment. That's what allows you to steer. So if you look at a photo of our test rocket underneath the parafoil, you can see it's actually gliding through the air. It's got some horizontal motion, and so that's how we're able to steer, which gives you more control, but also gives you some more risk. It's definitely more complicated dynamics. And then looking at our deployment sequence, it's also new for us this year. Usually we use 2 separations, and we deploy out of those. This year we're just doing 1, and we're doing a COTS tether release device. We're using the tender descender, which some of you might be familiar with. So that definitely complicates our deployment, and it's just another thing we have to think about when starting the recovery sequence.
So BLIMS is comprised of 2 bulkheads, and in between those bulkheads are a pair of spools. Those spools are mounted on a single shaft and powered by a single motor. And so by winding the brake lines of the parachute on each spool in opposite directions, as we spin the shaft in a single direction, we get those counteracting up and down force, retraction and extension, which then leads to the left and right banks of the parachute. You can see underneath the second bulkhead, we have the motor as well as all the batteries, the motor controller, and you can see a port down at the bottom there, which allows us to connect this whole system to our central flight controller, which is running our own flight software, which actually runs Trevor's lovely program and sends the signals. You can see in this cross-section here just a little bit more detailed view of those 2 spools. We're using a worm gear and worm to transmit the motor torque up to the shaft. This prevents backdriving, so as the parachute initially deploys, there's a pretty significant force, and this prevents that force from being transmitted back into the motor and preventing us from losing position. So to select an appropriate motor, we wrote our own software simulation that takes into account more actual motor torque curves, gear reduction of that worm and worm gear, as well as the spool radius and a few other factors that aren't plotted. It then generates a 3D grid of these points, and each point's color represents the validity of that certain combination. And basically by visualizing these 3D spaces, we're able to identify not just the motor that was most appropriate for what we were hoping to do, given the torque and speed requirements, but also where in that operating envelope we want to have it. And so this was hugely valuable. We'll talk later in this presentation about the iterations we've gone through, but having an underpowered motor has been a huge issue for us. And so actually writing this and taking the time to think about it was pretty essential to having a high functioning mechanism. Do you mind shifting the slide there? Oh, there we go. Yeah, so as I mentioned earlier, the BLIMS has to take the initial opening force as well. We actually used last year's launch data because our drogue ripped off and main deployed without drogue, which meant we had a pretty high loading, and so we were basically able to use that acceleration as a worst case scenario. And from that, we then drove our ANSYS static structural simulations, both on components as well as the assembly as a whole. So on the right here, you can see a photo of the actual manufactured assembly, those two bulkheads, the two spools beneath them, the motor, batteries, and everything beneath. On the left, you can see BLIMS hooked up to the parachute in the top right. The static lines are the big wide blue ones that you can see there, and then the brake lines, which are the ones we're actually tugging on, are thinner ones, which are a little bit hard to see, but running in between the two. There we go.
So now I'm going to talk about the software architecture. So this is an overview of our software system. So we have a ground station that sends our intended latitude and longitude where we input it in a website. And then that is sent over a wireless bridge to our fill station, which then through a cable connects with our onboard flight computer. This is all an SRAD system. And so this allows us to, on the pad, right before launch, send our intended latitude and longitude that we want to direct our rocket to. Next slide. So this is an overview of the hardware and softwares that we use. So we use a Raspberry Pi Pico that runs all of our flight software. The BLIMS software is fully integrated into that. And then we take in GPS data and altimeter data to then inform our decision for the controller that then sends a direct command for how much the motor should turn in either direction. This is an overview of our software execution sequence. So flight software, once the rocket ascends, main deploys, we then initiate the BLIM sequence. So there's a predetermined delay after the main parachute deploys to allow for the parachute to completely unfurl and settle down. We then initiate a turning sequence. So we take in the sensor data, we execute the controller logic, and then execute turning commands. And then we cycle this throughout the duration of the flight. This is an overview of our initial turning sequence. So we did a bunch of tests. This test was initially to just help us learn the behavior of the parachute. So if we turn, this much right or this much left, what does the parachute actually do? So you can see here we tested it in a neutral state, a little bit right, a little bit left. Saw if we could repeat that, and then bigger and bigger turns.
Okay, so Thomas has now described a mechanism that is capable of performing the maneuvers that we want to execute underneath the parafoil. Gabby talked about how we can then talk to the rocket when it's on the pad and actually use the central flight computer to precisely control the motor when we're in flight. So now the question becomes, how do we actually steer to where we want to go? So to answer that, I want to start with just some definitions. So if we know our own GPS location and we set a predefined target, which we send when the rocket's on the pad, we can call our bearing the vector from us to the target. So that's basically the way that we want to be traveling. Then the heading is the direction in which we are facing, and the track is the direction in which we're actually traveling. It's effectively your velocity vector. So I'm making that distinction because they might not necessarily be the same thing. For example, if you're in like a heavy crosswind, then you might have a situation where you're facing one way but actually moving in a slightly different direction. So the control variable that we really care about is the track. Behind me here is a block diagram of the controller. So this is the loop, the logic loop that's happening every single time step. So basically what it does is we have our predefined target and we have our current location. From that we can calculate the bearing, which is just the direction from us to the target. That is our target that we want to be facing in that direction, right? And then if we take our track, which is calculated with like a differential from in between GPS coordinates, then we know which direction we're traveling. And if those two vectors are not aligned, that is what our error. So that discrepancy basically is fed into a PI controller where your proportional control is kind of your immediate response to that. Anytime you're not directly traveling in the direction of your target, you're going to have some P term show up there. And integral term basically acts as your trim in the flight. So if you are being pushed by a crosswind, perhaps it is holding you slightly off the vector you want to be on, that integral term will accumulate over time and will basically allow the system to correct for that error over time.
Yeah, so I mentioned earlier that we've gone through a few evolutions of BLIMs. Here's kind of a layout of all of our different generations going all the way back to 2019. And what I want to emphasize here is that this system is kind of deceptively challenging. And we actually started with a 2-motor design and ended up simplifying it to a single motor design. So for a team that is considering building one of these in, specifically on this 2-motor, single motor point, we deemed, after actually jumping out of planes ourselves and talking with skydivers, that the added maneuverability of a second motor really isn't worth the technical the additional technical complexity. And so we spent several years trying to develop this 2-motor design. Packaging was really challenging. We ended up simplifying to a single motor design, and it's now working and quite well, actually. So this is just a point for anyone who is considering it, is think about whether you really need the added flexibility of a second motor and whether it's worth that development cost.
So this is a video of us drop testing. So up until last spring, we had not tested our ram air parachute, and there was a lot of different unknown factors, like could we deploy it correctly, could we package it correctly, and so we were very lucky. We got to work with a local skydiving company that willingly dropped a 100-pound metal tube out of a plane with a parachute that may or may not deploy. As you can see, we successfully deployed, didn't hit any cows, and this taught us a lot. I guess it showed that this parachute could be successful. We could use it for our system. But what we also realized from this test is that we couldn't fully simulate a flight scenario, which prompted us to actually create our own testbed rocket this year, which we'll talk a little bit more about later.
Yeah, and one thing I want to highlight is those large opening forces. We have a nearly 150-pound rocket, and so when that ram air parachute deploys, there's significant loading. And so in addition to the ANSYS static structural tests, we also built our own test rig. On the left there is a 2,500-pound winch, which we can apply forces for an extended period onto both specific components of the BLIMS assembly as well as the entire assembly itself. And this really was not only making sure that the components could withstand the forces, but also that the shaft wouldn't deform under those loads and cause binding later on in the operation. So this was hugely valuable because ANSYS and FEA in general can give you really precise results, but validation is equally as important. And so this was an important step in making sure that our simulation results were actually matched with reality.
And so, previous slide. In that video, it shows, this is us doing some software testing. So this is BLIMS fully integrated. In the video, you'll see on the left our computer that executes our code that connects to the AV bay. On the far left, connects with our motor controller, which then talks to our motor within BLIMS. So all of that then tells BLIMS how much to turn. And so as you could see, we could do a lot of testing on the ground here.
Okay, like Gabby mentioned earlier, we decided pretty early on that it was going to be really important to our design process to have a way to actually get this thing in flight. The way we did that was through a rocket independent of our competition rocket. So we brought up an L3 test platform and we launched it 4 times. You can see we definitely had a bunch of failures. So that's the first time we tried to launch it. It blew up on the pad. On the right there, you can see the rocket sitting in the snow. That is indeed the main parachute still inside the section. So we had a lot of problems with things surrounding the system, not just the system itself. You know, I talked about how we had that new deployment sequence for us. We definitely had some hiccups there that we had to deal with. This was just a really great way to get through that. But we also got a ton of great data out of this. So our second launch was the first one where we had some real success. This was the first time where we had our SRAD GPS driver working, so that allows us to get real-time GPS data that is actually going to be able to be fed into the central flight computer. This was also the first time we had our parafoil deploy with this rocket. So if you jump to the next slide there, we've got a video of it descending here, and you can actually see it performing a right turn just at the end. So it's a little tough to see, but right before it touches down, BLIMS pulls on the right brake line, and we actually execute a maneuver. So that's the first time we've seen the rocket actually turn. That was a huge milestone for us. The next launch where we had a lot of success was the fourth one. If you go ahead and jump to the next slide, yeah. So here's the GPS trajectory from the launch. At 1,500 feet there, our main parachute opens, and all of those little zigzags is BLIMS turning the rocket. So that characterization sequence that Gabby was talking about earlier, that's what we're doing here. We're trying to see how consistent are we when we pull this amount, how much does the rocket actually turn? So this gave us a bunch of really good information about that, and I mean, it's just super cool to see that we could actually turn, you know, that was really great. So here's kind of the top-down view of that trajectory. You can see after each maneuver is called out there, we have a clear turn. Something that's really important to note is how susceptible we are to wind. So all those little points is basically every time our track vector is more than 90 degrees away from the wind direction. So at that point, we effectively stall. We have no more forward motion. That's a huge limitation on our system. If the wind is strong enough, we just can't travel upwind. So the way around that for now is from a mission planning perspective, trying to choose points that are downwind. You know, luckily we can change our target right before we launch, so we can kind of get an idea of what the wind is looking like, choose a point downwind. Additionally, the controller is tuned pretty conservatively. You know, it is a skydiving parachute. You can do sporty, aggressive maneuvers, but the goal here is really to have more kind of conservative, slow movements to get us facing the way we want to be.
So this is a video from our test launch from about a month ago. We're showing this not because BLIMS is actually running on this. We had a false start, which corrupted our altitude data. And that meant that we, instead of using our flight software, onboard flight software, we used our backup system. That really is important because BLIMS runs within our flight software. If flight software doesn't run, BLIMS doesn't run. We've since corrected that and are now able to fix that on the pad if we do have a false start again.
So another tool we use to try to understand the parafoil, you know, the dynamics are really complicated. So we made a simulation in MATLAB that is really simplified. So this is just considering a 2D plane and some torques. We have the torque applied by our asymmetrical drag caused by us pulling on the brake lines. We've got a small drag torque in there just resisting our motion. And then that wind restorative torque term is kind of representing the fact that the parafoil wants to orient towards the downwind vector. Basically, this was useful to kind of understand what is like a step response going to look like. If you jump to the next slide, here's an output of where we're running a P controller. So like you can see, there's the undershoot characteristic of a P controller, and that causes this behavior as you get closer to the target of an increased input over time. So this was kind of built based off of our empirical data to try to match that as close as possible, and it gave us a starting point when tuning our gains, and also just let us understand, you know, how is an undershoot going to affect us? What do we need to be considering when we're actually choosing a target, kind of things like that. So the last step of testing the controller was we put it in a car and we drove it around and saw what it did. So on the left there, that's a visualization of the data coming out of the controller real time. If you look at that blue arrow, that's our current heading. And if you watch as we steer over the target bearing, the system will respond. So right now we're too far to the right and the left brake line pulls in. That's inducing a left turn back towards the center there. If you watch the P and the I terms, the P term is responding immediately to that, while the I term is slowly integrating that error over time. So this was a good way to validate on the ground the ability of our controller and the logic in general.
Yeah, so at this point, we have a mechanism which has been tested in flight and we know is robust to those high opening forces and is able to execute those calibration turns. We have a controller which is able to steer us in that direction, which has been tested on the ground. And so tomorrow, we're really excited to launch this system with both of those married together and actually guide to a GPS waypoint for the first time and hopefully not end up in a tree. Thank you all for coming. Find us afterwards if you have any questions. We're Team 700, so also feel free to stop by our booth. But thank you.
All we tell it is a GPS target of where we want it to land. And at every time step, the microcontroller is calculating what's the bearing to that target, what's my current track, what is the error there. And that error gets fed into the PI controller, which is continuously running.
So the correction may be different depending on how far off track.
Exactly. Yes.
And is it, what's the effect of it? Does it actually extend your time of descent because you're zigzagging?
Yes.
Does it get you down faster?
So it kind of depends on what it does. The glide ratio of the parafoil is a function of how far you're pulling the brake lines. So the larger a differential you're creating and the more you're turning, the faster you're going to descend. So in a situation where we start very far away and we turn a bunch, we will hit the ground in a shorter amount of time. But if we open and we're already facing where we want to be facing and we travel there, the controller hasn't done very much and we'll just kind of be in the nominal position of our parachute where we're just straight gliding. Yeah, in the back. Yeah, so that MATLAB dynamic simulation was kind of like the starting point. So all of the torques in there are kind of based off the empirical data that we saw in those test platform launches. You know, we could see like, okay, we're pulling the brake line 3 inches. We are turning at this rate. Like that was kind of the response of the system. And then we could basically build our MATLAB simulation around that. And then when we run the controller logic in that simulation, we get kind of an approximate place of where to start with like what is the proportional gain we want to start with. And there's also, you can start with like, well, if we're 90 degrees off of our target heading, we want to be at a max amount of pull. So you can choose your gain such that when you're at that error, you have that amount of input, you know. Yeah.
So if your track
Sorry.
is like, just like back to like descent time, so if your track is pretty similar to your bearing and you just glide over, and so your descent is slower,
Mm-hmm.
if the rocket, I guess, overshoots, will it circle back to like land in that exact position?
Yeah, it's a great question. It's definitely something that could be improved upon further, like a state machine and kind of different behavior depending on where you are in your flight. As of now, if you overshoot, the error is just going to spike. And so, you know, you can imagine if you have basically no error and then all of a sudden you have 180 degrees of error, it's just going to try to turn around, right? So there's not super sophisticated logic about like performing some sort of spiral at the end. But that's definitely something that could be added in the future. Yeah. Yeah. There's a risk there of hitting the ground too hard, right? So we don't know exactly what it looks like when we spiral at a certain amount. So yeah, that's also a great point. And for that, you need 2 motors. So that's kind of a future iteration that we could think about is if you can pull on the brake lines independently, now you have kind of like a pitch control, right? Yeah. I think in the back, yeah. So the GPS module is 10 hertz. I think the CFC is the same thing, yeah.
Every 50 milliseconds. So very fast, really as fast.
Actually 20, yeah. Yes, so it's a COTS like antenna and GPS module, but then we have an SRAD driver written for it, which basically allows us to get the same data that like our COTS GPS is using, but actually feed it into a computer real time. Yeah.
All of our software and electronics are SRAD.
So is the GPS point that's pre-programmed before flight?
Yes.
Can you excuse me, can you override that in flight, or is it once you set it, you have to go to that point?
No, we cannot. And that is, I think, for a few different reasons. Just for our setup, because we are doing it on the pad that is connected via the wireless bridge, and then the cord that connects from the fill station to our onboard AV bay. Once that rocket launches, we no longer have that connection. I think it's also like a competition requirement that we do not change that location because we do not want it to become a missile.
Yeah, so as of now, the plan is get out there, see what the wind direction is looking like. Then we are going to set it to a distance that is chosen based off of our previous launch. So we want to see it overshoot just a little bit to kind of understand what happens when that situation happens. We're hoping that, you know, we track towards the target, we overshoot the target, and then we're able to turn around and get back towards it. Yeah. Yep. So, yeah, in our test launches, we have not yet put the whole system together, you know. So we've done the controller testing in a car, trying to simulate the flight, and then we've gotten the actuated mechanism in the flight. So we have not put the mechanism with the controller. That's first time is happening tomorrow. Yeah.
Cool. I think we have 30 seconds left, so we'll wrap it up there. But thank you all for coming, and yeah, hit us with any questions later.
Thank you all.
All right, hi everyone. I'm Sahaj and this is Koi. We are from the UCID rocketry team, and today we will be presenting Candlebark, a hybrid rocket engine simulation suite for high-powered student rocketry. Today we'll be taking you through a background into hybrid engines and the team's history with hybrid propulsion. We'll then be taking you through the internal models that make up Candlebark. We'll then also take you through the rigorous testing and validation that we have conducted through internal tests, unit tests, external validation, and finally a flight test in order to validate the performance of our software, and finally how we applied our software to our IREC 2025 entry into the 10,000-foot SRAD hybrid liquid category, Project Podium. So a little bit quickly about hybrids. Unlike solid engines, which fuse their oxidizer and propellant into one singular grain, oxidizers have these separated. Typically, this looks like a liquid or gaseous oxidizer and a solid fuel. This results in a quite much more distinct thrust curve as compared to solid engines with similar impulse, where the majority of thrust is produced during the liquid phase, and a sudden drop-off is seen during the gaseous phase. This presents a new set of challenges when it comes to designing a launch vehicle around a hybrid engine. A quick bit about how the team's history with hybrid engines overall. Our journey began in 2021 with Project Waratah. This was our first subscale hybrid engine and laid the foundation for our understanding of hybrid propulsion theory and hybrid engine design. This later carried on to Project Waddle, an N-class hybrid motor, which also saw the development of our permanent testing facility, which allowed us to conduct hot fires of all our 3 hybrid engines. Both our knowledge of these 2 research hybrid projects then led to the design and testing of the Podium engine, our first flight-scale hybrid engine, which, unlike our previous hybrid engines, had much more finely tuned performance parameters, which were increasingly modular due to the engine's concurrent development alongside the launch vehicle. Now, the primary challenge that we face and hybrids in general face, especially when transitioning from something like a research project to one that's considered primarily for a launch vehicle, is the high variation of hybrid engine performance based off ambient temperature and the overall environment, where small changes in temperature results in fairly large deviations in the oxidizer mass that can be loaded during the filling of the engine, which thereby significantly impacts impulse and therefore the apogee of the launch vehicle. The UCID rocketry team has conducted a series of fill tests throughout our testing campaign of the engine and seen small deviations in temperature result in fairly large deviations in mass. Now, current solutions or simulators that are available in order to solve this problem and allow us to better model hybrid engines range from student research and designed softwares to commercial softwares. Now, while commercial softwares may offer increased advanced performance and increased model complexity, the paywall that is often associated with these effectively make them unviable for a student team such as ours. And current student research and design softwares such as HRAP, OpenThrustPy, Novice, and HybridPy employ fairly simplistic models to do with their nitrous modeling, their internal ballistics, which could be improved by the team. However, the team sought to utilize a hybrid simulation software and package it with further down the line with trajectory solvers that would allow us to create an end-to-end software pipeline to accurately and effectively simulate a hybrid launch vehicle from the conception of its engine all the way to its launch. And therefore, we found that no commercial or SRAD options met our requirements, and hence we moved to inventing or creating our own simulation software. Now, given that Candlebark, which is named after a native Australian fauna, hence the lovely flowers you guys can see, is based off 4 major pillars. Firstly, upskilling, ensuring that our software is able to condense and capture as well as teach our undergrad engineers and to do with combustion and fluid dynamics. The second is to do with creativity, A core tenet towards Candlebark and our hybrid simulation software was to ensure that the complexity of our hybrid engine designs was limited by the capability of our engineering capabilities rather than the quality of our software. Next, accessibility. As a student team, we wanted to ensure that undergrads of any level could understand, utilize, and further progress this software, and hence it was written in Python, which is taught as a first-year course at the University of Sydney. And finally, legacy. We wanted to create Candlebark not purely as a software that could be used for the current project where it was modeled, but more so a tool that was decoupled from the current project and could be used by the team, continually advanced and continually progressed for more complicated and sophisticated hybrid designs as the team continued to progress with its journey with hybrids. And now I'll pass it on to Coy to take a bit more of a deep dive into the methodology behind Candlebark and the internal models that allow it to have a greater performance as compared to current SRAD options.
So everybody, my name is Coy. So Candlebark is divided into 3 core control volumes that encapsulates all aspects of hybrid rocket engines. We have the first control volume, which is nitrous dynamics, responsible for simulation and modeling of how the tank drains and how nitrous evacuates the tank and how that affects the temperature, pressure, and molar composition of the tank. Secondly, we have the internal ballistics module, which is responsible for the regression rate calculations, gas dynamics, and how our geometry evolves as a function of time. Finally, we have our nozzle flow module that is responsible for calculating the thrust force given the exhaust gas dynamics. I'll be focusing on the novelties of Candlebark, which is focused on nitrous dynamics and internal ballistics. The nitrous dynamics can be broken into 2 core main logics, which is the tank drain and the injector model. So for Candlebark, we employ a non-ideal, non-adiabatic model, meaning that we account for the heat transfer processes within the tank. So in Candlebark, there are a couple different heat transfers occurring. Firstly, you have the temperature differences in the phase of the tank. You have the liquid and the vapor that are interacting with each other, as well as the liquid to the tank wall and the tank wall to the ambient, as well as the liquid evacuating the tank. Secondly, for non-ideal effects, we employ a non-ideal equation of state, meaning that we are able to account for molecular interactions within our gaseous phase, which has given the team much better simulation modeling capabilities of pressurants in the system, which gave us the flexibility to design systems that can go into that sort of regime of pressures. Nextly, for injector modeling, simulation and modeling of the injector flow is perhaps the most crucial component in quantifying hybrid rocket engine performance. And this is extremely difficult due to the high pressure drop experienced by hybrid rocket engines, and hence you often have phenomena such as two-phase flow and choked flow. Now, there is no encapsulating model that captures good nitrous flow across all flow regimes, and hence Candlebark is dependent on casework. For example, if all liquid has evacuated the run tank, the single-phase incompressible model is defaulted to because the fluid is inherently singular phase, and furthermore, the pressure convergence has satisfied enough such that single-phase incompressible becomes valid. However, during the liquid phase, or perhaps the most critical component of the engine burn, there exists 2 conditions. If Candlebark detects that the flow is choked, we employ a compressible mass flow rate model that caps the mass flow rate past beyond a critical flow regime, a critical pressure point. However, if the flow is unchoked, we then extend upon the single-phase incompressible model with the homogeneous equilibrium model, which addresses errors in two-phase flow effects caused by the single-phase incompressible model. However, the downside of this model is that beyond its critical point, it predicts a reduction in mass flow rate for increasing pressure drops, which makes it inherently anti-physical. So then we implemented the Dyer model, which is the best of both worlds, because it is a dynamic weighted average of both the single-phase incompressible and homogeneous equilibrium flow, dependent on the bubble growth rate time of the liquid. So then Candlebark, for every single time step in a simulation domain, can, depending on the pressure drops, fluid dynamics, and characteristics, is able to dynamically choose which model it solves for nitrous flow. So now finally, we have the last cool feature of Candlebark, which is its ability to extend past circular port simulation and modeling. So Candlebark has a couple of ports geometries built in. However, the user can import in a CSV document containing the geometry that they want as X and Y values. This has allowed unprecedented creative freedom in terms of hybrid rocket engines, and it has allowed UC Rocketry team to explore many unique and different port geometries in their design cycle. Candlebark can handle the collisions of multiple ports elegantly, as well as handling the phenomena called sliver burning in singular finosol ports. Meaning that as the port shape evolves, there are certain parts of the field grain that touches the boundary first, and hence that part has depleted, and in the engine, the field grain is subdivided into smaller parts. As you can see in the top graphic, as the field grain touches the boundary, we have a significant amount of thrust drop-off, as then there's less available mass flow rate because of that sliver burning phenomenon. And Candlebark is also able to capture that very effectively. So now I'll give the mic back to Sahaj, and he will discuss about how we validated all of our softwares.
So now that we've gone through the overall methodology behind Candlebark, we also engaged in a rigorous testing campaign to ensure that our novellities were allowed Candlebark to have a boosted performance compared to other viable public options. Now, firstly, we did engage in unit validation, for example, with our nitrous modeling, which fused our tank draining and composite injector modeling through multiple co-flow tests, and we found a good agreement between experimental and theoretical data. We also utilized co-flow tests to derive our injector discharge coefficients to further boost the accuracy of our model. We then engaged in a rigorous testing campaign throughout 2024, especially with our Podium engine, where we engaged in a vast array of very different engine configurations, varying our injector area, our fuel grains, as well as our nozzle throat diameters. And despite these very large deviations or changes in our engine configuration, we consistently saw with our latest model of Candlebark a very, very good agreement with experimental data. And comparing this with University of Tennessee's commonly used hybrid simulation software, HRAP, we saw a consistently much better agreement with Candlebark as compared to HRAP with our experimental data. It should also be noted that specifically for hot fires 10 and 12, more complicated engine configurations were hot fired, namely reduced infill density of an ABS fuel grain, and secondly with hot fire 12, a much more a pseudofinosol fuel grain, which HRAP could not support. To ensure once more that we created a tool that was decoupled from the engines that it was modeling and developed off and validated against, we also engaged in a rigorous external validation campaign where we used publicly available data from hybrid rocket engines that were made by student teams and research groups, and what we ended up seeing was a very similar amount of error and agreement with our overall impulse. So this is the unexploded ordnance by Waterloo, Phoenix 1B by ASRI, and Archimedes by Rice University. And finally, to translate this into a launch vehicle, we also compared Candlebark's prediction of Podium's launch with the experimental data of a thrust curve derived from the accelerometer data from our flight computers. We found with our Telemega, our primary flight computer, a less than 1% error in the thrust curve and our overall impulse, and with Raven, we saw about a 10% error. I'll now pass it back to Koi to discuss about how this tested tool was now utilized to solve the main design engineering problem of Podium.
Yep. So since Candlebark and Podium were developed concurrently with each other, during the early stages of the design process, Candlebark was not available as a tool to be used. So hence the team reverted back to using HRAP to size all their propulsion systems. And one of the main criterions for sizing is to have an adequate pressure drop in order to have like good combustion stability, which is something that the team has experienced in the past. So now, since HRAP uses the single-phase incompressible model, as previously mentioned, for large pressure drop regimes, it tends to overpredict mass flow rate, and hence, since we sized everything based off of that, it drastically undersized major components of our propulsion system, and hence Podium, for the majority of 2024, did not reach its target apogee and other target performances. So then Candlebark was then implemented to resize the propulsion system, given the constraints that the casing of the engine and the tank has already been manufactured previously. So the sizing scheme of Podium is automated, given that the user inputs in the constraints of the problem. In our case, that we have constraints on the maximum length of the fuel grain, the diameter of the fuel grain, the maximum injection area, and its maximum chamber pressure. We also have target objectives that we can put in, such as the target apogee of the system and trying to reach closer to stoichiometric combustion of ABS and nitrous oxide, which is 5.5, which is something that we've also been struggling with. So Candlebark, based off of that, generates a design space, and since it's a multi-process operation, it is able to complete 10,000 different design configurations within the hour, allowing the team to have unprecedented flexibility and creative freedom to pick and choose the engine design configuration that works best for them and their engineering limitations. So the red dust curve is the inaugural hot fire of Podium that occurred in early 2024. It is a 2,000 Newton engine with a 12,000 Newton second impulse. And then the black line is Podium engine after Candlebark has revised certain parts of its components. So from there, we have a 2x improvement in our peak thrust and a 3,000 Newton second improvement in our impulse, meaning that we had a 50% increase in our apogee just based off of resizing 3 key components in the combustion chamber using Candlebark. And that is, we increased the injection area by 50%. And then with the fuel grain specifically, we were able to extend past using circular ports and then used a pseudo-finisole, which is that shape, that is our current fuel grain that we're using, something that was limited to us by the usage of other softwares. And finally, we were able to also figure out the right chamber pressure for us to operate at using Candlebark, such that we maximize performance while still retaining the adequate amount of pressure drop for negating combustion stability. Given that we have resized our engine, we then have a nominal flight path for Candlebark. From a nominal flight path, when we integrate Candlebark with our 6 degrees of freedom trajectory simulator, IREC, and that gives us a full end-to-end simulation of hybrid engines and hybrid rockets in general. From this, we're able to conduct a Monte Carlo analysis of our nominal flight path. And apart from traditional inputs into Monte Carlos for sounding rockets, we have such as dry mass, center of gravity, and launch rail angle. We were also able to incorporate hybrid-specific aspects to this Monte Carlo simulation, such as fuel grain density, the ullage factor, meaning how much we filled the tank to, and fluid temperature, all of which, as previously mentioned, are extremely sensible variables that have a drastic impact on propulsion performance. And having the capability to include these factors into our simulation allows us to fully characterize hybrid rocket engines in general. And finally, we have integration with our data acquisition and control software. So Candlebark, in tandem with our direct simulator IREC, is used to generate a lookup table of mass and temperature, and then from that, it predicts an apogee. This script is then loaded into our ground control software, and then taking in a pressure transducer reading and a load cell reading, we're able to determine the apogee of the rocket during the propellant filling sequence. And from this, we're able to dynamically target how much oxidizer mass we put into our rocket engine, such that we can accurately target 10,000 feet on the day, regardless of ambient conditions. This also has improved the rocket as a whole, as we're able to bypass complexities such as active control mechanisms. So to run through the presentation to conclude, firstly, we introduce hybrid rocket engines. UC Rocketry team's involvement in hybrid rocket engines as a whole. There's challenges and how other teams have endeavored to solve them. We then presented our own personal solution, Candlebark, how it works and its novelty features. Finally, we demonstrated that our simulation has a high degree of fidelity across all engine performance configurations, regardless of whether it is UC Rocketry team's own or external validation. And finally, we demonstrated how it can be used as an extremely powerful tool in the design cycle of hybrid rocket engines and how it gave the team a significant advantage going into IREC 2025. And any questions?
I have a question. At the very end, you highlight moving away or not harpering on active control mechanisms and opting for a more propulsion-based solution to reach 10,000 feet. Why? And maybe you can't speak to it as a full team, since you're maybe just doing propulsion. But why is that separated? Is it in the future? Are you planning to do active control as well, or is this just like another stepping stone in like your software suite and in your construction? Like, what's the thinking there?
Yep. So the overall design mentality of the team in general is to minimize the complexity of what is on the rocket and achieve the best performance with the minimal amount of complexity for our launch vehicle. So without employing any active control systems such as air brakes, we sought to use simulation software in order to optimize performance, something which would have a much greater control authority.
So with using cooling as your control system, have you looked at how well calibrated your load cell is and like how much of a confidence interval you have in your oxidizer mass and how that relates to apogee?
Yep, so we've done a lot of testing regarding our load cell. So what we do is we do Christmas tree tests, meaning that we continuously put load onto the load cell within its linear regime and then take load off to like fully characterize how well our load cell operates. We also tested a bunch of different like setups, and we're able to like sort of interchange the way that we set up our load cell to work best for our system. And we're very confident that our load cell can get us to within like very, very reasonable values to be used to have this control mechanism.
Do you have like an offset or a range that it'll give you like close enough to the value and kind of what that translates to at peak? Like, are you about 100 grams off either way, and will that get you within a couple hundred feet, or like how accurate is this?
Yeah, so basically a load cell deviation, I guess for our load cell, is within, well, plus or minus like 0.02% of its maximum load rating from my memories. And that is basically within the nearest like less than 100 grams of difference. And when it's less than 100 grams of difference, that is within less than 100 feet of apogee, like uncertainty for us.
Yeah.
So maybe not specifically applicable to Candlebark, but for if you're controlling off the fill, is your fill automated, or are you manually reading these values and controlling how much you're filling?
Yep. So at the moment we are working, we have implemented some automated fill procedures, and we are working to better improve this at the moment. But given, I guess, highly variable temperature conditions, sometimes the behavior of nitrous warrants manual intervention. But yes, the idea is that by integrating Candlebark with Lacebark, you are able to effectively include or incorporate a target mass, and from there the automation fill procedure will target this target mass.
What feature improvements do you see for Candlebark?
Yep, so for at the moment, the biggest assumption that we have for Candlebark is our regression model is non-dimensional, meaning that we don't account for variations
Testing. Is this good now? Okay. So I can start. We can go to this slide. Okay. So hybrid rocket propulsion introduces a more complex system than traditional solid rockets. There are active fill sequences, multiple stages of operation, involving many points of control and necessity for a real-time feedback. Operators aren't just lighting a motor, they have to interact with the rocket throughout its life cycle. These systems demand extensive software control and allow for more active decision making throughout the launch process. While we try to mitigate much risk through operation procedures, there are increased risks with electronic control and just some that we have to mitigate. Now, why is precise control timing essential for a safe operation? In hybrid rockets, timing isn't just about performance, it's about safety. If an anomaly like overpressurization occurs, the system must react immediately. That means commanding vent valves or actuators like our main engine valve or fill or vent valves within milliseconds. Any delay in aborting could cause catastrophic failure, especially during fill when tanks are pressurizing or range operators are working with the system. Critical sensor latency too matters too. For example, if software is reading old pressure data, the fill operator could be making decisions based on outdated values, potentially leading to wrong decisions and dangerous outcomes. Along with latency, the system must also ensure that the data communicated over wired and wireless links are not corrupted, and this may also misinform the operator. Reliable real-time critical actuation isn't just nice to have, it's a foundation for safe operation. One of the biggest risks in any launch operation is operator error, especially when dealing with high-pressure fluids and ignition systems. For example, the main engine valve cannot be opened arbitrarily during the fill process, leading to an uncontrolled flow. Additionally, some processes must occur in a specific sequence, such as the main engine valve must open after igniters have been lit. Finally, if communicated data is corrupted, then we must be able to account for this and avoid showing the operator this data. In hybrid rocketry, increasing the number of sensors may seem like a simple design choice, but it significantly impacts both system complexity and operational safety. First, there's notably an increased system overhead. More sensors demand higher data throughput and consume resources. The system must acquire, filter, and respond to sensor inputs in real time, which introduces challenges in scheduling critical commands that can switch between handling and collecting sensor data and being able to stop this process and switch to more critical commands. Now that we've addressed operational issues, there's also software and electronic systems issues that we must address. We must consider the failure of our own systems and put mitigations in place to avoid harming people and the systems themselves. Without clear, timely communication from the rocket, the ground operator is essentially flying blind. Losing telemetry mid-fill or with a pressurized rocket or just before it launches can create uncertainty and put hardware and people at risk. Intermittent power issues may automatically turn valves to their default state and potentially injure operators during fill or cause unpredictable behavior during rocket flight. Unhandled bugs and memory issues can freeze or crash the system. In embedded systems without proper fault isolation or watchdogs, this can stop all control, leaving valves stuck open or closed. These systemic risks inform every part of our software design choices, from preemptive scheduling to watchdog timers. The next slides will show how we mitigated each of these with deliberate architectural decisions. Okay. Our system had to be designed to handle sensor data collection, storage, communication, and react to real-time commands like valve actuations. These conflicting demands necessitate a reliable and deterministic operating system architecture where tasks are scheduled based on priority and timing requirements rather must be enforced and not by brute force or manual logic. A real-time operating system, for context, is designed to perform operations in a precise amount of time, respecting well-defined deadlines. To meet these needs, we built our own operating system around free RTOS, an open-source real-time operating system kernel. The kernel facilitates interactions between hardware and software for the computing system. More importantly for us, the kernel facilitates concurrent execution of multiple tasks, including sensor data collection, actuator control, debugging, and communication. Now we need Now we needed to use this as a base and create a system that would give us deterministic behavior on startup, while running, and when each thread communicating with each other. Leveraging C++ polymorphism, we were able to create base classes and define generic structures for the behavior of each of our tasks or threads. Each task is a singleton, ensuring that each instance runs at a time, which improves predictability and prevents duplication of critical operations. Tasks extend from the base to serve specific roles while maintaining core behaviors like safe initialization and standardized execution and a shared communication protocol. This generic structure ensures that our system behavior is deterministic. Next, we needed to ensure that while multiple tasks or processes would interact with each other in a deterministic way, we enforce standardized inter-task communication through command objects that encapsulate both instructions and data payloads. Each task has its own dedicated queue, and other tasks interact with it by enqueuing these commands. This ensures thread-safe, isolated data handling and avoids concurrency issues such as race conditions. Hybrid rockets require control and telemetry, and this inherently adds more points of risk. The role of software, in addition to providing functionality and information to actuate operate the system, is to mitigate these risks where possible. One way to mitigate the risk from both operator error as well as potential uncaught issues with either software or hardware is through a state machine. This maintains our procedures, ensuring operations happen at the correct time and allow us to add functionality to maintain safety, such as an automated abort. This ensures deterministic control logic. It enforces valid transitions. For example, if we were to go from a pre-launch to a fill state, we want to ensure that all the valves in the rocket are closed. The software system will ensure that this happens automatically when the operator wants to start fill. Similarly, from any state of our rocket, if there was any issue and we were to abort, the software system will automatically take care of actuating all the valves open and depressurizing the rocket, relieving the operator of this. Okay, so it is inevitable that we have any power loss or intermittent power failures, and these can be pretty dangerous. Without safeguards, a reset would return valves and systems to their default states, which can be unsafe. For example, vent or drain valves opening mid-fill or mid-flight. To solve this, we implemented state recovery by saving the current system state to onboard non-volatile flash memory. On power-up, the system reads the stored state and restores it immediately. This ensures that the rocket never unknowingly enters an unsafe configuration after a power interruption. We tested this feature thoroughly and achieved a fast recovery time of 50 milliseconds. That speed is critical. It means the rocket can quickly regain its correct state without missing transitions or triggering invalid operations. Overall, state recovery provides a vital layer of resilience, allowing the system to handle unexpected power failures safely. To operate a hybrid rocket remotely, we need a communication system that is both lightweight and resilient to faults. This includes handling corrupted data, confirming command execution, and ensuring that all systems speak the same language. What this means is, on our rocket, we use C++ with a serial data communication, and in different parts of our ground systems, we use like Python to handle the data. It can be really easy to write different code and define data formats separately, which could mean you don't handle your messages correctly. Hence, we chose to use protocol buffers. Protocol buffers let us define our data structures once and generate parsing code in C++, Python, and any other languages. So essentially, we use a proto-language, we define our message formats, and then we just generate the message payloads for every language we possibly use. This guarantees that every node on the rocket or ground interprets telemetry and commands consistently and safely. No manual parsing is needed or ambiguity. To define clear message boundaries, we encode every message using COBS, which is consistent overhead byte stuffing. This removes any 0 bytes in the data payload and makes it easy to detect the start and end of every message. Every 0 byte there delineates between data packets. Every message includes a 2-byte CRC, which is a cyclic redundancy check. This ensures the data integrity of the message. If any bit in the message is flipped, we can use the CRC and confirm that the data is corrupted and ensure that we catch this error before displaying it to the operator in the GUI. Important control messages like valve actuations require acknowledgements before the user interface can update. This closes the loop. No command is assumed to have been executed until the system explicitly confirms it. If a message is dropped or corrupted, the operator is notified and can retry. Although altogether, these components, protocol buffers, COBS, CRC, and ACNACs, form a layered protocol that ensures reliable communication and a fault-tolerant system. In any system, we design to assume certain failure, and we have to ensure that we have mitigations in place. For example, communication interruptions due to RF interference, radio failures, software crashes, or unexpected hardware faults. To address this, we use a watchdog timer that expects regular heartbeat messages from the control backend. Each received heartbeat resets the system timer, indicating the system is alive and responsive. If the heartbeat is lost, whether due to communication failure or a crash of the system, the timer expires. When that happens, our rocket state machine that I previously talked about will automatically trigger an abort, opening all the valves in the rocket and saving the system. This watchdog heartbeat is a critical failsafe that ensures that if something goes wrong in communication or in the software, the rocket safely transitions to a known and reliable safe state without relying on human intervention. Finally, our software has been validated and tested through real campaigns. We've observed our watchdog trigger correctly on telemetry loss and saved the system, and our rocket state machine has effectively blocked unsafe commands from operators. Recovery time was impressively fast with 50 milliseconds, demonstrating the robustness of the design. The combination of an RTOS, thread-safe execution, a rocket state machine, and a reliable communication system gave us a solid real-time architecture capable of safe and predictable operations, even in uncertain conditions. These features have already proven their worth in live tests, protecting against accidental risks. Finally, for future work, building on this foundation, our next step is to implement DMA, direct memory access communication protocols. This will offload data logging from the main CPU to the dedicated controller. What this essentially means, I mentioned before, we have a lot of sensors we need to collect data from. If we use a DMA controller, the CPU, we can offload this overhead to a separate controller, not the CPU, and we can use the CPU time to perform more critical operations such as valve actuations, also improving our real-time response. Additionally, we'll continue improving the system by profiling our memory usage to optimize performance and increasing testing coverage to ensure reliability under all conditions. Ultimately, these efforts will make hybrid rocketry safer, more reliable, and more scalable, ensuring that we can prevent catastrophic failures while maintaining full control over complex operations. Thank you for listening. That was my presentation. Yeah? If you guys have any questions. Yep.
Yeah, so you talked about free RTOS implementation
Yep.
on your system. Could you go a little bit more into that, like what kind of scheduling algorithm you used there, if it was like deadline monotonic or rate monotonic or
So,
that sort of stuff?
so we are just using like the default baseline scheduling algorithm, and we are relying on setting up free RTOS with the priority of our tasks, and then we're just relying on the base kernel scheduling of the tasks to preempt. But yeah. And then we also, like, I guess for more specific context, for like more critical actuators, we like prioritize those higher. And then even when it comes to sensors, we have other onboard sensors like IMUs and stuff, which are lower priority since they aren't critical to operation. So we also have our sensors scheduled differently. So we always like rely on having the most important thing to execute.
Okay, cool. And then, so kind of off of that, like, how do you, you might have mentioned it already, but the resource management, like if you have a critical resource that one of your sensors needs to acquire,
Yeah.
what kind of deconfliction are you doing there?
We're just using mutexes.
Okay.
Yeah. Anything else? Yeah.
Do you have any file system for storing your last system state? And if so, how do you prevent data corruption if you have like any power loss while you're trying to write?
So yeah. So.
Make sure to answer with the mic up.
Oh yeah, sorry. But yeah, so for the state recovery you mentioned, we separate our flash chip into two sectors, and then we do redundantly write it in two sectors. So as you can see from the diagram here, if we fail to read from one sector, we'll read from the other one. We are making the assumption that we have written the state because when the operator changes state at any point, we write it whether there's a failure or not, so we don't wait for a failure to write it. The system state is written, like the last system state, whenever change is already written. So if there were to be like a race condition where as soon as the operator pressed like the next state and there was a power shut off, then that's like not in our control. And yeah, it would just recover to the last known state. But yeah. Yeah.
So, did you do any sort of like system level analysis with before and after? Like here's our risk. You listed them out at the beginning, but like here's our risk, here's the consequence, and then after analysis of here's the mitigated risk and the mitigated consequence. Did you do any of that?
No, in all honesty, for this one, we kind of had like a layout of like our requirements and risks, and we didn't really have a system in place before to compare it to. So this is just kind of what we started with, and we've just been going off of that.
But you had requirements that you had.
Yes, yes. Yep.
Another question. Do you do any profiling of your RTOS or like seeing how like tasks like context switch as well as seeing how much time they spend in it?
No, which is why I had that in the future work is we haven't done any we haven't used any explicit tracers or debuggers to like actually like show the trace and time of the context which is happening. We've just been more relying on like just practical testing. So we'll write our own like unit tests or whatever to like confirm that the switching happens according to the way we want it. But we haven't explicitly like had a timing diagram, a real-time timing diagram, because those also do require like pretty expensive tracers.
So just a heads up that Sanger does. If you asked, you could probably get a
Yep.
sponsorship with them.
Yeah, we are trying to get a JTrace Pro. Yeah, right now. But yeah. Any other questions? Well, hope you guys enjoyed it. Thank you.